So, okay, thanks everyone for being here today. I mean, I'm very kind of pleased to share what it's taken me so long to learn. And hopefully today I'll be sharing some material that helps you in any time of your career. You have like a decision of going through like a systematic review. So hopefully I can share some advice on how to perform these systematic reviews. And this is not there's not a unique way of doing these kind of things. And what I'm going to be sharing today is just the way that I did it, all the mistakes that I did, right? And what I've learned about all of those mistakes, and try to save you guys a little bit of time. If at any time, any point of your career, you kind of decide to guide the systematic review or like just do it by your own. So all the things that we are I'm gonna be sharing today with you, it's posted on GitHub. So as I was telling previously, is this the URL? Just locate that URL in your computer, or just simply go to github.com/ my last name Giordano N, and then locate the repository. The repository name, so you probably first will go there and then just locate this repository, systematic reviews in R. And for downloading the repository in your computers, just simply click on code. And then we click here where it says download zip, right? That will download the folder. Just place the folder wherever you want. I'm not gonna download it because I already have it on my computer. Once you download the folder, just extract the files. So you have the folder there. All right, so this is how the folder should look like. You guys all there? Just simply open up the R project file. So as to follow. I mean, there's no need to follow like live today. I mean, all the material is published. It's published there. It's publicly available on GitHub, so you can just simply open it up, right? Just want to give a chance of you guys, whoever wanted to follow live, have it there in your computer. Okay, let me open up this HTML file. All right, so I mean, to get started and give a little bit of introduction on what systematic reviews are. So scientists, we think that we are supposed to generate agreements on how things look like on our world, but all of we generate is disagreement, right? So there's a lot of disagreement on like certain topics, right? So the idea of like these systematic reviews is kind of to summarize all of that disagreement and like kind of review what literature said, right? But just do it on a systematic way. So there are several ways to conduct reviews. These systematic reviews tend to be like unbiased, right? So we are try to like cover like our reviewing literature, right? But in a systematic way, right? So if it's systematic, if Luis doing this review and if I'm doing the same review, we should come out with the same result, right? So we are supposed to like apply an objective method for reviewing literature. That's what a systematic review is, right? So we tend to like we'll try to do something that's unbiased, right? We call it. So as I mentioned before, this is just a simple code, right? That summarizes some of my experience while conducting a systematic review. And so, okay, so the first thing we need, right, when summarizing literature is just a simple question, right? So I don't know, Gustavo, He also went through kind of like a systematic review approach. So we want to share the question that you were trying to answer.
Yeah, so one of the questions that we tried to answer, was the effect of application of sulfur, affect the yield and the protein concentration in wheat production.
All right, well, Gustavo, he just mentioned like effects of sulfur fertilization in on wheat yield and protein, right? So, all right, so in the question that Gustavo had there are like probably 3 pronouns there kind of important. So the first thing we got to do when conducting a systematic review is go out there and see what we can find for people that have been studying sulfur fertilization in wheat and impacts on wheat grain yield and protein concentration. So again, this in my own experience, what I did, I went to Scopus, right? That's a database that contains thousands and thousands of publications. So you can use this link that's on your HTML file that will get you. Oh, sorry, here. So I'm open it on a new tab. This link will get you to this advanced search that these databases do have, right? So let's try to come out with the question that Gustavo was having, right? So he in his question, he mentioned like right away, like 3 pronouns, right? 4, right? It was sulfur, wheat, protein, and yield, right? So we need to like write a query that contains at least those words, right? So there's several ways in which we can write out that query. So one of them, we're gonna search for those words in the title, for example, right? So we're gonna write title here. And we're gonna search for the word wheat. And probably either yield or protein. And or sulfur. Or sulfur, right? Well, I think British English, they write it differently. So we're gonna just click on search. So Gustavo, he did his first search in his systematic review, right? And well, we got 15,000 articles, right? So, well, Nico, if you just change here a single word, you'll probably come out with different articles, right? So instead of, let's say we miss one word of sulfur and, well, it's accounting for that one, right? But anyway, well, if we change probably like whether we are putting or an and here, right? We're gonna be changing the amount of articles that our search will be giving out. So, and well, I'll tell you later. So when I started my own review, as Gustavo, we had a simple question and we got the pronouns from that question and we just dumping it there in Scopus, right? And we searched for those articles that were exploring the effects of late season nitrogen on wheat grain yield and grain protein concentration, right? So what we did basically here, we click here where it says all, right? You can just select that, and I think it's you download here. No, sorry, it's export. There, export. So you click on export, and then you can download some information about those articles that's related here to like several features, right? Like for example, the author, right? We have the title, and then we can also download information about the abstract, right? So yeah, so in here we select a format. We can select this RIS format, That's the one that our library, I'm going to show you later, handles in R. And we can export those articles, just download that same file with this search that Gustavo did. Right? So let's go up to our software now and try to go step by step. So first thing we're going to do before getting started with this RevTools package that helps us. So the thing is here, we're going to go through a few now. The first search, we got almost 15,000 articles, but our final review, we won't have 15,000. At the most, we'll have 50, 100, I don't know, not that much. So we need to apply certain criteria, right, that we need to define previously to kind of filter out those articles and keep only the articles that we are interested on extracting information, right? Because there are many of those articles might be analyzing effect of sulfur fertilization, I don't know, on environment and not reporting yield, right? Or I don't know, they might be reporting spring wheat, right, yields and no winter wheat, and maybe you're interested only in winter wheat, right? So there's certain criteria that you need to define before, right, to kind of like funnel down from those 15,000 articles into like your articles that you're going to use for constructing your final database. And so I'm going to just run the packages here. Most of you, if you guys are coding live, you might need to install this Pacman package. That's basically what this package does for you. It just tests whether a certain package is already on your computer. And if it's not, it will install it. But if the package there, it would just call the function library. So I'm not going to run it because I already have it here on my computer. And just run library and run pload for loading all the packages. If you guys have any problem, well, Emma and Gustavo will be around and can help like with any coding issue that you might be having if you're coding live here. And load some custom functions, please. Just load the whole chunk. All right. So as an example here, it's this query, right? This is the query that I use first on the systematic review that we conducted as part of one of my research projects, right? So if you can just copy paste it and try it on Scopus. This query, what's basically it's searching for different journals, right? So in our criteria, we were interested on making sure that we were targeting articles that were published in high impact journals. And we were searching on the article title for a certain query that contains the words wheat, nitrogen, protein, and yield, and only for those articles that were published after 1980. So we decided to put this threshold after 1980. As you guys know, I mean, the Green Revolution has been something like it changed the way that we cultivate wheat. So, and it changed like a lot of like things regarding how the crop works. So we were interested in looking at semi-dwarf cultivars and not necessarily previously released cultivar before Green Revolution. So in our query, we include this threshold of like date that was having somehow an agronomic meaning. So let's in the folder, so you're gonna be let's take a look at what the folder that you download, right? So here it's hopping to articles, right? So in the folder that you downloaded, you have these articles already search folder. And I'm gonna tell you then later the story why they were like previously searched articles. But you have this file, that's the file that you are supposed to download from Scopus, that has this format: Research Information System Document, RIS. So this RIS file, if we go back to R, we can just simply load these functions, right? And read this file and load it into R. All right, so here we're looking at this RIS format file, which when we first download it, I mean, what's the format of this file? I mean, it's like, what is it an RIS? And it's not more than a data frame format, right? So what this allows us, it's to like have the information of each of those articles on a single row, right? And we can uniquely identify all of those articles by the DOI, right? Already. So what we did, right? So I'm gonna step into step 4 and then I'm gonna go back, right? So what we did there, we loaded first we downloaded this RIS format file, and we went to this package that's called RevTools, that it helps you handle that selection that I mentioned before of applying certain criteria for determining which of the articles you were going to be selecting, right? So here, well, let me tell you something, right? So why this library, I think I found it so powerful. This comes out to like, I spent like almost a year doing this systematic review. After a year, one of my like co-advisors, he reviewed the article and he said like, Nico, I mean, I'm sorry, but I think you need to go back and do the search again, right? So, I mean, doing the search again for me was starting from the very beginning, right? So for me, I need to figure out a way to kind of have track of all the articles that I already searched, right? And kind of like only search for the articles. I mean, the problem is like, he told me, Nico, you need to go back. You need to change an item on your search query, right? The thing was, we were searching for articles that they were containing words only, that query I mentioned only on the title. And he said that you should search for that same query for words on the title and the abstract, right? And what ended up happening, it's that we were first looking at 1,800 articles, and now this search was getting us like 5,700 articles, right? So a huge amount of numbers. But there was a lot of effort before done by searching those 1,800. So I told myself, I'm not gonna search those 1,800 articles again, right? I'm not gonna look them again. I need to figure a way to like uniquely identify all of those 1,800 articles that I searched for only words on the title, right? I'll remove them aside from this big database. So see if there's a marker here to make terrain, right? Well, anyway, no worries. And so we were having from these 5,700 articles. Now we were almost with this app would allowed me to reduce, come down from 5,700 to like 4,900 articles, right? So which is 3,000, almost 4,000 articles. So which is a huge reduction on effort that you need to put if you got to do the search again, right? So here in step number 2, it's like kind of this anecdote, right? It's just a simple thing, just running the same thing that I mentioned before, but changing the search query to the title, abstract, and keywords, right? And I did the same thing, right? I downloaded this RIS file, and I'm just loading in R. So let's take a glimpse here. It might take a little bit to load. But it should be okay. Right, so let's see. Okay, so now we have these 5,700 articles all on the same data frame here, right? And taking a glimpse, we have the title of the article, the year in which the article was published, the DOI, that's like a unique identifier for each of the articles, the author, and the abstract, right? So from here, I mean, what these RevTools app does, the one that I mentioned before, is basically allows us to read this table on a friendly manner, right? So it just simply reads this table on like a web version, right? So you just like reading Facebook, I don't know, or reading anything on the internet, right? You just read this table, and it allows you to, at the same time, it's going to be writing a new column at the very end of this table that will have like a yes or no, whether you're going to be selecting the article to keep it for your constructing your final database, or excluding the article and not reading the article anymore. So let's take a glimpse. And well, this is before stepping in there. So this anti-join function is one of the joins functions. It's merging two different tables together. And the anti-join, what's doing, it's those rows in which the DOI is matching, they're going to just be removed aside, right? So we do like a merge of these two. Let's take a look at these two data frames that we have now. That's the first search. So we have like almost 1,700 observations. And then if we run the same function and take a look at the second search, right, we have like almost 6,000 observations, right? So each row, it's an article, basically. So the anti-join, it would be just those 5,900 observations minus, we just remove the first search from that final database, right? So now we don't need to be looking at, let's open it up here. And now we don't need to, so you see, now you have almost 4,000, right? So we don't need to be looking again to articles that we have already searched, right? And that's, I think that's something very, very powerful that we can incorporate on a systematic review. Based on like, we can change the search query as many times as we want. And we can try to see what's the query that will come out with the greatest amount of articles, right? Without the need of having to research and look again those articles that we have already scanned and we don't know that they are going to be part of our review. So let's open up this, let's run this screen abstracts function. That's the one that opens up a Shiny app. And this Shiny app, it's the one that basically, I was saying, it's just a way of taking a look at that data frame, but in a more friendly manner. So the Shiny app, you can open it up here in R, or just simply open it up on the browser. You're gonna browse for a file, and I'm gonna just make sure you can look it on your computer where it is. I think it's this one. I think it's this one. All right, so we're basically looking there at the first row of the table, right? So where we have the title and the abstract, right? So, this won't follow Gustavo's question, right? Because the query, I already downloaded the data, so I don't need to do it here live, right? So this is following a different question, right? But in the case of Gustavo, he'll be looking whether this paper is having any treatment, like sulfur treatment, right? And if they are taking any measurement on yield. So probably what Gustavo will be doing first is like doing like a kind of like an abstract search to test whether the paper is more or less lined up to your question or not, right? So does Gustavo has the variables that he needs in the paper or not, right? And then we kind of further apply more and more criteria. So for example, let's say, well, this paper, we can just, I'm gonna just randomly do like a selection, right? Just exclude a paper, right? And then let's say we find an interesting paper, and this paper, we are not sure whether this paper is gonna be included or not in our final database. So I just type in here, I'm not sure. Or you can be consistent and type in there like specific features that you find in that paper, in which you like can then later filter and search for something specific, right? I don't know. For example, let me give you an example here. So I was, as I told you, the systematic review I conducted, we were assessing the effects of late season nitrogen in wheat crops on grain yield and protein concentration, right? And of course, nitrogen, it's not only late season nitrogen what matters, but really matters the nitrogen that we apply early in the season, and also the soil nitrogen that we have at plant, right? So I was having some papers that they were, some of them were reporting that early nitrogen, some others they were not reporting yet, some others were reporting that initial soil nitrogen condition, some others they were not. So I was taking like systematic notes on that. So I was putting, I don't know, not soil and right. So those papers not reporting soil nitrogen, I was not sure at the very beginning whether to include them or not. So I was kind of putting consistently putting the same note on those papers to go back again and like revisit again those papers to make sure that they were going to be included or not on the final database. So, well, anyway, so we can just, I'm going to just type in that note, save it there, and this one we can either maybe select it because it applies to the criteria, but it doesn't have like a minor, maybe this minor thing of having the soil nitrogen. And here, just by reading the title, this is radiation insufficiency of sunflower crops, right? So you just exclude this one, right? So there's, at the very beginning, you can just do like a very quick search. And then, I mean, once you get trained, you figure out like, okay, maybe what I need to search is not I don't need to read the introduction of the whole paper. I just need to go to the middle part of the abstract and go through the methods of the paper and quickly just glimpse the methods of the paper, and that would tell me whether I need to include or exclude the article on my final database. So, and this one it might be, so I select this one, right? So whatever. So then once you spend the whole day doing a search and you screen like, I don't know, 500 articles, well, better not, maybe you just do, you just save the data, right? I won't say do it at the final stage of the day, but just do it more recurrently so as not to lose everything. So maybe you can type in here the date of today, and then you put, well, search, I don't know, underscore, and you save the file as a CSV. So if you go to the folder, right, and There we go. So that function, what it does create is a CSV file that has a column at the very end that contains NAs for those articles that they weren't searched already. And then you can just filter those and just filter the ones that you selected or excluded, right? And there you go. Those are the ones that are gonna maybe, the selected ones are the ones that maybe they're gonna be part of your final database. So this app, what helps you is to come down from almost 5,000 articles down to probably 100, 200, you know, something, a reasonable number of papers that you can maybe print and like revisit in detail to see if they match all of your criteria that you're using for including articles on your final database. Something that we haven't talked is about that criteria that we are applying to filter papers. That's very case specific. So I won't say that what I did, it will also work for what you guys are going to be doing in the future. So we're not gonna visit on that. Okay, so let's keep going. So probably I have some example data I'm gonna be sharing here. It's a database from a paper that they were assessing the effect of splitting nitrogen applications on wheat grain yield, right? I mean, what if we apply nitrogen altogether, we split that application in two, or we split that application in three? What's the impact on like nitrogen, crop nitrogen indicators and crop yield and that kind of thing? So let's just take a look at this data here. The paper belongs to Hugh et al. 2021, that's the link to the paper. And these guys, they were very friendly and they just published the data set that they collected. So if we take a look at this data, we have a column in which we will. So again, I'm going to just back up a little bit and not go too fast, but maybe for some of you guys it's the first time. So once we go, we use these screen abstracts, right? We go revisit some of the papers and make sure that we have, I don't know, in my case, we were having 47 papers as part of our final database. So we went to those papers and okay, we are going to extract information and data from those papers and put them on a table so we can analyze that data, right? So fortunately, I mean, I'm not saying here that there's like a unique way of doing this. There are several ways of doing this, but I will try to give some advice on how to construct this table, right? Which is a crucial step for then making your life easy during data analysis. So the first column, you put a unique identifier to each of the articles, and you can have a column here in which you put a unique name to those articles, right? Try to write those names on the way that it goes. I mean, using uppercase and all the like the letters. I mean, as it should be, right? Because that column is the one that you're going to be using later for plotting. And my own experience, my own mistakes is that I need to rewrite that column again, and sometimes it takes time. So if you do it from the very beginning, right, it will save you time later. And maybe, well, a column with the year, the journal from which the article was retrieved, a column with the country. This column with the country, you might want to search those libraries that R has for that do contain the country shapes and name it on the same way, right? Because if you name, for example, it's not the same of naming USA, US, or United States for them matching those columns with the shape of the country. And I'm saying this because probably if you conduct like a meta-analysis or something, you'll come out with a figure on your paper that will show where those studies were conducted, and you probably want to paint the shape of the country and those kind of things. So make sure you name the countries on the same way that are named on that library that you're going to use for plotting later. Okay, another thing is the location here. And the location, it's not only important the place, right? That I would say it's a minor thing, but it's a very important thing is to have a column with the latitude and longitude, right? In metric coordinates. Having these two columns, it allows you not only to do that plot that looks nice, that you have the map and the studies that are coming from different parts of the globe, but also allows you to retrieve weather data, right? So nowadays we have these global data sets that we can use carefully for retrieving weather data and try to explore associations of our response variables and environmental attributes or in those places. And Cesar, I mean, you work in soil science. I mean, I know that there's like global soil database, and right, and there might be even, I mean, I think I can't remember the name, but I think there's a library in R that you can use for accessing these global soil databases. So, I mean, what I see here is like retrieving the latitude and longitude for that's the specific location in which a trial was conducted, allows us to get at once with just few lines of code a ton of environmental attributes, right? Describe the environment, how things were going on, how that crop grew up, right? So that's those are two columns that were at least for me, I think they must be in all databases, right? In all methodologies. So before going through what's going on here, I'm gonna step into, right? I'm gonna go to the columns that really matter, right? That's the one that we are gonna be putting there, our response variables. So, what's going on? Sorry, guys. That was weird. Okay, let's back up. Yeah. So, okay, let's catch up again. That was weird. Eh? And yeah, so we're gonna have in our database two columns in which we're gonna be putting our information related to our response variable, right? So in meta-analysis, we'll be doing this comparison of like coming back again to the example that Gustavo was mentioning. Gustavo might be retrieving information from those papers from the control treatment and the sulfur fertilized treatment, right? So ideally here, we should have that data on a wide format in which we have a column that contains the yield for the control treatment, another column that contains the yield for the sulfur applied like treatment. So in this database, I can't remember exactly how these guys they were doing the comparisons, but I think they were comparing. They were doing several comparisons here, but one of the columns, this one, yield underscore kilograms an hectare one. It's the one that contains yields in those treatments that nitrogen was applied all at once. And then we have this other yield column in which nitrogen was split into two different moments of application, different timings, 3 timings and 4 timings of application, right? So you'll see here that there's a bunch of missing data, right? So the guys from the very beginning, they were very optimistic and they say like, okay, we're gonna try to make as much as comparisons as we can. So they collected as much data as we can, right? Like, so once you do the search and you are already retrieving data from your articles, try to be optimistic that you're gonna find all the data that you're gonna be looking for. Never mind if it's from, if you have that data from some papers, or if you don't have it from some others. But just be optimistic, because then later, one of the things that you can do, you can just subset those data sets and use smaller data sets for answering specific objectives, right? So we have that column that contains the observed yield value, right? We have another column that contains the number of replicates that the trial was having, and another column that contains the standard deviation, right, of that observation. So I was talking to Adrian Correndo once, and he was very simple in the way of defining a meta-analysis. Like, a meta-analysis model is no more than a model that is weighting the observations by a certain measurement. In this, most of the time, it's a measurement of error, like the standard deviation, or you can weight those observations like by the number of replicates that the trial was putting there. I mean, and what I mean about weight of the observation of the studies, right? It's just giving different importance of the study depending on, like, the amount of error that those studies they were having. I mean, just to give an example, and I don't want you guys to compete, but let's say like Luis was conducting a study with, and Luis, you were very unlucky, right? And then your data came out with a ton of like residual error, right? So the data, and then, I don't know, Claudio, you conducted a very good study in sulfur. Both of you guys conducted studies in sulfur, and the study of Claudio came out to be a very good study, you know, very precise. You were able to measure and capture all that variation. So the weight of the study, it's the inverse of the measurement error, right? So the study of Claudio will have a higher weight on our pooled effects, our mean, than later, right? Because I mean, Gustavo, Claudio, you did the things right? But Luis was unlucky, and he like had more error. So as we have, like, what they say, like, we can have confounded factors, a way to account for these confounded effects, not factors. Confounded effects is to weight the observations by a measurement error. So these guys here in this database, they already have this standard deviation metric already there. But what you guys should do is to write out a column with the measurement error that you are collecting from the study, right? Maybe it can be standard error, standard deviation, it can be feature least square difference, or the honest, I think it's square practice honest HSD, whatever. Yeah, so there are several measurement errors, and there are functions in R that are available for us to use for free, that we can use them for transforming those measurement errors into a unique measurement error as standard deviation, as these guys have here. So, yeah, that's the information that they collect, right? So, coming back to what the trial, I'm thinking about the idea of Gustavo on conducting a systematic review. So we have the thing of many times in meta-analysis, you'll hear about moderators. So what is a moderator, right? Or what's a meta-regression, right? So that information that we're going to be using for analysis of moderator, categorical data, or analysis of continuous data, meta-regression, right? It's those factors that we're going to be extracting for the paper that we are going to be aiming to answer a specific objective, right? So these guys, for example, they were wondering for some reason if, I don't know, the soil texture, is it the soil texture related to whether we're going to see an effect of splitting the nitrogen rate or not, right? I don't know, I might be like towards maybe coarser soils are more susceptible for leaching, right? So in those coarser soils, we might be able to see that response in splitting the fertilizer rate, but in soils of fine texture with more clay, I know they have the ability to mineralize more nitrogen, right, and retain that water more, hold that water a little bit more. So maybe in those soils we don't see that response in terms of splitting the nitrogen rate. So in this case, right, this is a nice variable, soil texture, right, because we can either retrieve from the papers categorical data as classifying the soils in between loam or sandy or clay soils, right, in 3 categories, or we can simply extract from the data, maybe if it's available, the amount of clay content, right? So instead of having like a soil texture, we can have like clay content, right? So like a related variable there. So we make our data continuous and not categorical. You got to be very careful when analyzing categorical data and make sure that the categories are well balanced for avoiding confounding effects at the end, right? So the problem here is like if we stay on the logic of this thing of like we're gonna see work in the hypothesis that we're gonna see more response in coarser soils, but maybe I don't know, in those coarser soils they also irrigate, right? So are we seeing a response that related to coarser soils, or is it like an irrigation thing? Is it like a soil texture thing, or is it an irrigation thing? So we need to be aware that when analyzing categorical data, even continuous data, I mean, even continuous data, we are going to be subject to this thing of maybe looking at a thing, not necessarily looking at effects of the factor that we are analyzing, right? So does it make sense? Or let me know, you guys, if you have any question, you know. Okay, so I wanted to keep here again on the database because I think it's something where there's a ton of things to dig in here. So you'll see guys here. So I mentioned this about like weighting the studies, right? According to this measurement error. You'll see some of the studies, they do have missing information, right? So I posted for you guys, I think the paper should be somewhere here. Well, I haven't put that paper here. Yeah, well, it's not that one. Let me just pull it up here in Sotiro. You guys want? No, it's not that one. It's another paper. It's a very good paper, and Javi Fernandez, he was the one that mentioned this paper to me. All right, it's right here. So this is the name of the paper, and it's titled "Using Multiple Imputation for Estimating Missing Data in Meta-Regression," right? So these guys, they are people that just develop a method for in those places in which that standard deviation column from here, back here, was having some missing values. So we can imputate those missing values depending on how much missing data we have, what's the pattern of that missing data, if it's missing at random or if missing not random, right? And that can allow us, like, depending on what's our situation, how much missing data we have and what's the pattern of that missing data, we can put some data in there, right? Because if we have a ton of missing data, I mean, if we have, so these guys, they have somehow of like an analysis in which they were comparing two situations, right? They have a complete data set and they remove information from that complete data set, right? So they were comparing outputs from a complete data set and outputs from a data set with missing information. And they end up with some numbers there that you guys can go through. I can't even remember the numbers now, but that if you have a whole lot of missing data, it's the same of imputing the data or just removing the data. You'll get to the same output, right? And also depend what type of missing data you have. Are you missing yield observations? You might be in a bad spot. You might just remove those papers. Or are you missing standard deviation observations? And that's where this method becomes very powerful for estimating and imputing, putting there, though that standard deviation information. So, and when I mention this thing about the pattern of missing data, it's not the same of having a single paper in which we are in that single paper, we are missing, like maybe it has 10 observations and we are missing 3 observations within a paper of standard deviation, right? And a different thing is having a paper that was conducted, I don't know, in Russia, and in Russia, that paper is not reporting standard deviation units. So it's way more difficult to imputate the paper in Russia, right, than to imputate the paper from which we already have that some of the standard deviation information, right? I don't know if that makes sense, more or less. So the pattern of missing data matters, and also matters the amount of missing data we have for applying these methods. So make sure you go through kind of like those checks, right? Of like that to see the pattern of missing data you have and the amount of missing data you have, to see whether this method is suitable or not for imputing that missing data. So here, these guys, the same as the guys of Hugh et al., these guys that I mentioned before, Ellington and all these guys, they published the code for doing this multiple imputation technique. When I first started reading this code, I found it very, very hard. I mean, it was written on like a previous version of the package. So all the functions names were different, right? So I need kind of to figure out like what they were doing in each of the functions and everything. So what I ended up doing, it's a very simple function for implementing this multiple imputation technique. So this multiple imputation technique, it basically, we will select first a data frame that contains the columns with complete cases and with missing cases, right? In our case, our response variable is yield. So we're gonna select those yield columns, yield observations and standard deviation of yield observations. And we are going to be using the distribution of values that we have on our complete case column and use that distribution for imputing values on the standard deviation. So it will do that like, I think on our paper, we do it like 1,000 times. So we generated 1,000 imputed data sets and we got the mean there. And I think, no, from those 1,000 imputed data sets, what the function does, it removes the extremes and it keeps the ones that are under, I think it's the 2.5 and 87.5 quantile. And from those, not 1,000, but a little less data, imputed data sets, you take the mean. And then you impute those means here in these places where you have missing values. So let's, just for the sake of an example here, and I'm gonna just run, we're gonna run the average would be of 10 minus removing the extremes, right? Data frames with imputed values. So we run this function. It's very simple. The first argument here, well, you guys can follow, but this, the first argument. The first argument of the function is probably the number of imputations that you wanted to do. Here you should use a high number, 1,000. It works okay. And then here you'll pass the data frame that contains only the variables that you are interested on imputating on. So Gustavo, in your query, you were having yield and protein. So you'll do yield first. So you'll select your yield columns with your yields observations and the standard deviation of yield observations and run the function, right? This multiple imputation function. You will rerun the function again for your protein, right? So you select the columns that contain the protein control, the protein sulfur fertilized, and your the standard deviation for the control and fertilize. And run this multiple imputation function. So basically what this, this function was doing, we are column binding the data we have at the very beginning with two different columns, right? The output of the multiple imputation function and using the method described on the paper is just a column with all the complete cases. So let's take a quick look here. So you see, guys, here we have this standard deviation 2 column. And what we are doing in this standard deviation 2 imputed column, we are only imputing the values, the cases here, where we have missing information, right? And now we have a measurement error for those papers. All right, so let's see if I'm missing anything here. Yeah, well, again, the case, in case you have a ton of standard, it's very common to miss this standard deviation information from the paper. Not all the papers are reporting that information. So what you can do is to weight those observations by the number of replicates, right? So, and that's a different method. I don't know, it's very likely that Claudio, you are having less residual variance on your experiment because you were capturing that variance by number of replicates, right? And Luis was being very unlucky because he lost 1 rep. He got 3 reps. If he lost 1, you were only like using 2, whatever, right? So it's very likely that Luis would have more variance on his experiment just because he was having less amount of observations, so replicates. So maybe if you have a lot of standard deviation missing information, you can use the replicates. That's another approach. I haven't used it. In my case, we use standard deviation units for calculating the weights of each of the studies. So now it's just simply some data wrangling here. I'm gonna just run this whole chunk, and we are basically renaming some of the columns. We are removing some other columns while dropping some rows in which we have yield missing information. And down here, we have a function that's basically the pool variance. You need the pool variance for running the RMA model. That's the model that from the metaphor package for meta-analytic data, right? Basically, the pool variance, what it is, it's like a single variance component for the control treatment and the fertilized treatment, right? Most of the time, you will see, sometimes they do the control and the fertilized, they share the same value because the studies, they are not reporting separately the variance for the control treatment and the fertilizer treatment. So they share that value, but sometimes they do not. So you need to kind of run this function for having this full variance column that you're going to be using later for in your model. And well, and the weights, right? So the weights, it's the inverse of the variance in this case, right? So let's take a glimpse here. And go here and read a little, go through a little bit of like this RR function, what it is, column, what it is. So this is basically the response ratio or the natural logarithm of the response ratio. It's no more than dividing the sulfur fertilized column, but by the control column, right? And applying the natural logarithm to that ratio. So there are several ways in which you can calculate this response, right? A response can be simply like a mean difference, or we can standardize that mean difference, or there are several ways in which we can do this. I highly recommend to go with a response ratio or a measurement of the response that you can back transform to units that we actually read and understand. Because if I read a plot in which the response variable is the standardized mean difference, so what the heck is a standardized mean difference, right? How do you translate a yield standardized mean difference? It would be the yield response per unit standard deviation, in what that means, right? So it's kind of hard to interpret. But the response ratio, you can back transform the natural logarithm of the response ratio to just a simple response ratio, right? So that's what it is, the response ratio. And now it's, well, hands-on. Most of the meta-analysis, were you able to get the marker or no? No, there's some work. Okay. No, never mind. I can show you a plot. I can show you on the screen. No problem. Oh, okay. So most of the meta-analysis, you will see that they have this. They report this plot, right? That's called forest plot that has article 1 here, the author, I don't know, Cesar, et al, and then we have Luis, and then we have Claudio. And it's basically, so you all guys conducted the same experiment and then we have Gustavo, right? You all guys conducted the same experiment of testing the sulfur fertilization effects on wheat grain yield, right? So what we have here on the y-axis, right? This is our response variable. It's no more than the response ratio, right? And we can express this response ratio if we back transform it in percentage, right? So, Cesar, you found that either way, you apply or do not apply sulfur, it was the same, right? So probably you have in the mean of your trial, we will be overlapping 0, but you have some variation depending on location. Then Luis was able, we said that Luis was having a very low weight, right? Study of Luis. And he found that there's pretty much sulfur works very well on wheat, right? So Luis found like a good response, sulfur response on wheat, but with a lot of variation, right? Well, maybe too much. And then, well, Claudio, he did a very good trial and with little variation there, very little effect, but with very high weight. And then Gustavo and something average there, right? So the model that I'm going to show you what I have here. This is what we did. Right, so that figure, we're just simply seeing that forest plot in which we have all the authors, and we are assessing here our response variable, our y-axis, right, here horizontally. And now here in yellow is the pool effect, right? So the first thing we do when we go hands-on into a meta-analytic model, we write our model, right? So it's our response ratio would be equal to an intercept, right? A beta zero. And a beta zero is just simply would be zero, right? It's our pool effect, right? And we have that beta zero will have a variance, right? Our credible interval or a confidence interval, whatever, depending the model that you're going to be using later, right? So what we found in our case was that late season nitrogen was increasing grain protein concentration by 4%. That means that if the expected value when you apply the late season nitrogen will increase. If you have a width of 10% protein, you will come up from 10% to 10.4%, right? It would be a 4% increase in protein concentration. Yeah, so and well, this is what we report here, and let's come back here to R. So we have our response variable when we write the model. We have this bar column, that's the one that contains the pool variance and the weights, right? And here we are not specifying, I'm gonna run this. I'll take a little. We are not specifying any, so our model is very simple, right? It's response ratio equal to 0 plus some error, right? So what we're gonna be looking here, it's in this other example, remember that we are running the model of splitting nitrogen rates, this other paper, right? This is the estimate that these guys, they found for all the data they collected, the pool effect or the mean effect across all studies of applying I think they are comparing here, we are comparing splitting nitrogen twice versus applying all at once. It will increase grain yield by 0.02 units of natural logarithm of the response rate. So what we got to do there, we got to extract the coefficient and back transform it. And that's like a 2.4% increase in yield by splitting the rate. The thing is, so this is our most simple model, the one that we get started, right? So, but what actually is going on is we have some cases in which the response can be very, very high, right? And we have some cases in which the response can be low, right? Maybe, I don't know, I'm here. I did a trial and I found like a negative response, right? So, I mean, what actually is going on there? So, the next step is to start exploring all the data that we collected and try to make this model a little bit more complex. And now the response ratio will be a function of an intercept plus some regression, beta 1. And this would be what we call the moderator, right? that's an error. This moderator, as I was mentioning before, it can be, for example, a categorical variable, like the soil texture, either sandy soil, right, with 3 factors, as I was mentioning before, or a numerical variable, and we conduct a meta regression. Very well. So, all right. So the idea basically behind this, it's to explore what we call the confidence interval. What happens, I mean, even here in this situation, what happens, right? In this situation, what happened, right? What happened there that you were finding like almost no response, and then you were finding very, very high response. What happened there? So we can pass here moderator as a moderator soil texture, but we can use, for example, a category. We can classify all our environments, either in high precipitation environments and low precipitation environments. And we would expect, I don't know, we can expect that to see that response in environments that do rain, but when it doesn't rain, you cannot absorb nitrogen because it goes with water. So you will be in this area of your confidence intervals, right? So here, by one, you're going to be testing different predictors that might be helping you to explain whether what affects sulfur yield, your response to sulfur fertilization, or in this case, overall response to splitting that nitrogen rate. So maybe, I don't know, Gustavo, maybe you can give some comments there, but maybe it does depend on nitrogen fertilization, right? And you're going to be seeing that sulfur effect if you actually fertilize with nitrogen, right? So your moderator would be nitrogen. So you'll be having response ratio to sulfur, right? Would be a function of how much nitrogen you apply. And then you end up with a plot in which you have response ratio to sulfur, and you have your nitrogen, I don't know, nitrogen content in, I don't know, plant nitrogen content or total nitrogen applied, whatever, and that's like something like that. I don't know.
One of the moderators that we use for sulfur that we got a significant result was texture and for sulfur and organic matter. That was really affect. Higher we have the organic matter concentration, the significant response to yield was less.
You were using organic matter as like a continuous variable, or you were classifying it to like high and low?
High and low. So we put it less than 2 to 4, and more than 4. So we saw that whenever we have more than 4 on organic matter, we do not have the response. So if you do have something to check there.
All right, Lania, thanks for coming. Yeah, well, I'm of the team of every time that we have a continuous variable, we should be using the continuous variable and not make it like classifying the continuous variable within categories. Because there's a high risk when you classify within categories of being looking at another effect, and maybe it's not organic matter, right? And that's my feeling, right? That's so in last year, well, it was in 2021, Salt Lake City, that I presented the poster on the meta-analysis, and I was stating that if you apply that late season nitrogen at antithesis, you are having a greater effect on a greater increase in grain protein concentration. But the analysis I was doing, I was grabbing the saddle scale, and I was classifying that saddle scales in like 4 segments. It was from booting to heading, from heading to thesis, And then it was, yeah, a thesis to start of the grain filling treatment. And the studies that were applying the nitrogen anamthesis, they were increasing protein concentration higher, right? Due to that late season nitrogen application. Then by digging the data, I got some advice there, and just be careful with categorical moderators. They're very risky. And what ended up happening is that those studies that were applying nitrogen anamthesis, they were also irrigated, right? So we ended up thinking like, I don't know, we are not sure whether this is due to applying the nitrogen anamthesis or irrigating. So, yeah. So I don't know. It's just, as I told you at the very beginning, there's not a unique way to do it. And so it all depends. It depends on the nature of the data, but I'm on that team. So, but there's plenty of studies that they do. I mean, actually, the most famous meta-analysis, it might be that one that's called "When Does Not Till Yield More" from Cameron Peterco, and they do categorical moderators, and that's 1,000 citations. So, I don't know. All right. So next step is to conduct this influential studies diagnosis. The influential studies diagnosis, if we wanted to come back here to the same point, this point is very nice for explaining things. Because now let's say we're going to take Luis as an example. But let's say that he conducted the experiment and he got a response up here, right? And then the mean of our outcome, it would be here, right? So your model, you are modeling here, you are modeling this, you're not modeling your data, right? So there's a single study that's exerting a strong influence on your model outcome. If you model the rest of the data, probably your mean response will be somewhere here. Right? But Luis, we're right here. When you include Luis, right? So what you do there, that function that's you have it there muted, the Cook's distant RMA uni, it does like a leave one out study diagnosis. So it takes a little while to run it. I won't run it, but what it does, it basically, so you grab all your data and you remove Luis out, and then you feed the model and you get an output. And then again, I put Luis in and take Claudio out and see how the outcome of the model is. It's like a leave one out method. So you see how the outcome of the model is changing when you are removing a study at a time, right? And then you have some, I think I put here, well, we got to run this. We got to run the function on top for, yeah, for looking at the plot, but you got the papers here, and that plot would reproduce the same plot that these two papers, and they are recommending to look at to kind of test whether to remove that study or not from your analysis. And actually, it's not that you're gonna remove the study. Your forest plot will have Luis in the study in the plot, but the weight of Luis would be 0, right? So it would be a study with 0 weight on the final estimate, right? So you're not going to be accounting that study for your running your model. Yeah. I'm missing. Well, in my personal experience here, so I was running this, and I was having a paper by Tony Fisher, like it's one of the best graph physiologists, wind physiologists in the world. And that paper was like with a lot of variance, and was this diagnosis, it was detecting that paper of having like a strong influence on the final outcome. So I thought like, I mean, it should be something wrong, you know, like can be like these guys publishing crap. And I ended up going into even the criteria at the very beginning and looking into the criteria, and actually that study, the observations from that study that I was included, some of the observations, they were not matching the criteria. So at the end, yeah, we removed those two observations and that study that just came in, right? So it's just it's like a checking step that it's a safe word that you can do there. So just an if-else statement there for setting those study weights to 0, right? And here, this step, it is to run the moderator analysis, right? The moderator analysis is just simply writing this model down. It has the same syntax, very similar syntax as the LM function that you guys know how to run. So, yeah, here we set the intercept to 0 because we don't have a control texture that we want to compare against. I mean, we want to make comparisons against like different texture classes. So, I mean, we just run these. Might take a little long. And then there we go. All right, so yeah, well, here we have the estimate. So now we won't have a single estimate for all the studies, and we're going to have 3 different ones, and we're going to be saying that actually the response to splitting nitrogen or not, it would depend on whether we are on a clay soil, loam soil, or sandy soil. There's something important that I haven't told you. Most of the time when you are going to be reading a meta-analysis, they are going to be recording this measure that's called I squared. Right? There's a good example for here in this figure, right? That you don't need to even look at the figure, I mean, to tell you, to read the figure correctly to tell you what is the I squared. So we are seeing the response to late season nitrogen rates in different papers. So we have again, Cesar is somewhere there, Gustavo is there, you guys all conducted the same experiments in late season nitrogen, and you measure grain yield and protein concentration. What we found here is that you see the grain yield are the green colors points, right? Though all those points are all over 0, right? They are all overlapping 0. So the I squared here is very low because the variance across the different experiments, it's coming from residual error and not from variance between the different papers. So there's a very low probability of finding that this paper, it's very unlikely to find that actually these guys here, they were finding greater response because of like a specific treatment factor or environmental between differences between papers. If you look at protein concentration, the I squared here is very high, it's 84. And you start looking at the papers, they start finding different means, right? Those articles are sorted from top to bottom, from high yielding environments up to low yielding environments, right? And the I square, right, it starts telling us there that the differences between the papers might be related to actual differences, right, and not to random chance. So you see, grain protein concentration response to late season nitrogen is way higher, right, on high yielding environments on top, and it's lower on low yielding environments, right? It's like coming down here. So that's more or less the I square what's telling there. It's like whether there's a chance of finding differences related to actual differences between the studies and not to random chance. For yield here, the difference is that the variation that we see is due to random chance, and it's not due to differences between studies. For grain protein concentration, the variation it's coming mostly from differences between the different studies. So coming back to the example of splitting nitrogen applications, the I square here is very high, right? So actually, most of that variation is coming from differences between the different studies and not from random chance. All right, so, well, this is the way that I found it at that time, what to do, right? Probably would not be the way to do it nowadays, right? Maybe I will use different methods, but anyway. So coming back to this plot right here, one of the reviews that I received from one of my co-advisors was that I was having a plot and like this forest plot, and the confidence interval was almost on top of zero, right? Almost on top. But it was not overlapping zero. And my p-value was less than zero, was like equal to 0.49. Right? Oh, awesome. It's less than 0.05, it's insignificant. So he was saying that, I mean, we shouldn't be like looking at straight significant, not significant effects, but rather a distribution of, like, this would be, we should come out somehow with a distribution of, we should have a distribution of p-values, right? And so what I did here was like a resampling technique. So basically you resample the data and you run the model again and again. So if you run the model 1,000 times, you'll get 1,000 p-values. So you end up with a distribution of p-values that probably will look something like this. And from that distribution, you can retrieve the quantiles of the distribution, right? So actually, my p-value with a 95%, not chance, I wouldn't say chance, but this is not probability measurements, but would be within a range, right? Yeah, bootstrapping allows you to get a distribution of p-values and just try not to base inference on straight 0.049. So this function, what it does, it basically, it doesn't allow you much customization. I mean, you guys, if you wanna just do something more complex, you might just need to grab the function and customize it by your own. But you just take the number of cores your computer has for parallel processing, and you set the boot number. I mean, it's like the number of bootstraps that you want to get. Here I just put 16, but at least should be 1,000. And the function, if you will look at here, what's doing, let's see, these are the functions. So the function, yeah, what I wanted to show you, this is gonna save a lot of time. So what I'm doing here, I'm not saving the models on the environment, I'm saving the model on the computer memory. Because I spent like a ton of time, I was running the models and saving the models on the environment, and then the computer will crash or something might go wrong there. And then I found it handy to just store it there to like keep on working an hour later. And then when you load the model, yeah, you process and then you just load the model summary. Like here, for example, you read the model, but you just summarize it, and what you are saving in your environment, it's only, that's your, well, I don't want to use, maybe Joaco, you can help me here on some technical terms, but you're saving on the environment right here like a light object at the end, and you're not saving a heavy object. So the software doesn't practice. So at the end, we run this and we have this, the p-value actually for clay, it would be in between this number and this number, right? So we have that comes out from a distribution of p-values. And we can finally plot the data. Right? So it looks kind of fancy, the plot here, because we were only taking 16 bootstrap samples. But if we probably use 1,000, it will come closer to what actually is. So, yeah. So guys, that's all I have for sharing. I don't know if there are any question or anything you want to discuss, or I wouldn't use like this model and bootstrapping. So this VRMS package runs like Bayesian models. So you can put a Bayesian meta-analytic model to the data, and it will be the thing that I would do now. It's way simpler in the way that the package works. It gives you just like a posterior, and you just handle a posterior layer. This code is written down like manually. It took a lot of time to tune it up and make it work, and yeah. And yeah, it takes time to run also. When you run 1,000, so you remember, so we were running only a single. Well, I think maybe we can run this. So I think there's a clock there that will tell us how much it takes to run 16 samples. But anyway, it takes some time to run, so it's not as handy. But that's all what I learned. I mean, probably another good advice is if you are retrieving data from papers, be optimistic that you're gonna find all the data you're looking for and get as much data you can. Try not to go back to the paper. But what it takes time is to go back to the papers and understand the paper again, and like read the paper and understand how you need to extract the data from the table, And when you're doing all at once, that's straightforward. So that's a mistake that I did. I need to go back and forth to the paper a ton of times to retrieve variables that I didn't know I was going to be using later. Because if you look here, in the paper that we publish, right? So we have, in the y-axis, we have the response ratio. sorry, here it's the grain protein concentration response ratio. I mean, our response variable, as Gustavo had. And here we are having another, it's a different kind of model though, but it's not the same model, but we were having like a predictor. We were exploring association between the response ratio and Dow traits, right? So kind of like going to the milling quality, whether applying that late season nitrogen would have an impact on milling quality and Dow traits. So that was data that I collected at the very end. We were almost about to send the paper. I went back to the paper and said, hey, I mean, this could be a cool thing to look at. And went back to papers and collected the data. But at the very beginning, I didn't thought I was going to be using this data. We ended up using it, even though it came out from 1, 2, 3, 4, 5 papers, right? So from the 47 papers, we were only using data from 5 for this specific question. So that's why you got to be optimistic. Yeah. All right, guys. Any question? Yeah, well, that's a very good question. Well, yeah, so he's asking whether that I-square parameter was a unit, right? So it's like the unit is in percentage, basically, and it allows you. So what that percentage unit, it allows you to compare within different meta-analysis. Also, so you can do I-square comparisons between what I did and what someone else did, right? And because they are, so that way for accounting where it's basically accounting from where the variance is coming from. No, yeah. Yeah, exactly. Yeah. And there, I put a paper there that they discuss that and the importance of the I-square, and there are several other metrics. This tau square, I don't know how to explain it to be honest. But they are somehow like H square, they are somehow accounting for the same thing, right? Like quantifying variance. But you got to be in the I-square, you actually can compare between different meta-analysis. But if you look at the H square, you got to be more careful, because that might contain the unit that might have, it might be dependent on the response variable that meta-analysis is looking. So, I mean, it's nice. Yeah, it's actually, yeah, because it's the variance that's accounted by the random effects, right? Because studies are a random effect. It's like you are not interested in your model. That's something that I have included here for, actually I forgot, but but actually in the model you're passing studies as variance that you are not interested in looking at. So yeah, so it's variance coming in our case. So when we did the analysis, we were passing as a random effect variance that was coming from differences between studies, variance that was coming from differences between site years within studies, right? And variance that was coming from differences between genotype and management factors within site years within studies. Because so when you start retrieving information, I mean, for example, in our case, we were having data from the genotypes that these guys were using. And I don't know, it's very hard to quantify. I mean, how do you quantify it? I mean, Cesar's using one, Claudia is using another one, Gustavo's using another one. We are all using different genotypes, right? But maybe Gustavo, in your trial, you were using 4 different genotypes. So there's variants coming from there, so you can capture that. And yeah, that's the way that I found it, you know. It doesn't mean it's the only one. It doesn't mean it should be